Okay. So the first one is Nicole. She did before, and then we have Francis, and then...
My question is to Helen Blau. Congratulations for this beautiful talk. I have a comment about some new developments in the culture of stem cells. Because instead of getting cells which are differentiated, but that were in a monocouche, we have now the possibility to get tissues and even organs completely developed, completely organized as they are in vivo in culture by changing the way the cultures are performed. And I would like to have your comments about the future of these so-called organoids. They are called organoids because they are very small. They do not grow much. So do you think that it is a very critical advance toward regenerative medicine?
Of organoids is a tremendous development that may help with repair of lung tissue or intestine, that these cells will differentiate of their own when you give them the right bioengineered structures, make a big difference in addition to the correct cocktails of growth factors. And we're beginning to understand how you can make three-dimensional structures, and I think that's what you're saying, which is very important for understanding tissue engineering and also for maybe developing these tissues for transplantation. Yeah.
Okay, Francis.
I have a question for Helen and then a question for Eric. Helen, autologous cornea stem cells and the widespread applicability for that. I'm in the midst of a review of a proposal for corneal xenotransplants from pigs, and it has its ethical problems in terms of the potential of it works, immunosuppression, the transmission of porcine viruses. So my question to you, if I may, of what was a very clear, wonderful presentation, the opportunity of the advances that we hear here for distribution, for application to mankind. So where are you with this? Where is the corneal stem cell piece? Okay. Then, we ask one and then we ask the second, or how do we'll ask Helen's hand, and then I'll come back to, I've got a question for Eric. Okay, so thank you, Helen.
So that was not my work. I'm reporting on the field of the corneal transplants, but I think that tremendous strides in taking a person's own corneal cells. Yeah. Of course, we need a lot of work to scale that in order to make it cheap enough and accessible, but it's come a long way and it is available. It's been done in hundreds of patients now successfully.
Oh, that's the important point. So it yes. has been done.
Yes, it has.
Thank you for that answer. Eric, I've got a question on the dynamism of your technology. You brought it to the attention of infectious disease, but my interest is in ischemic injury, and so oxygen deprivation. And have you applied that technology to the event of an ischemic injured cell and to know of its restoration? So, we monitor ATP generation, et cetera, in our organ transplants to know that they have a functional capacity. But what of that by your technology in the deprivation of oxygen and restoration?
At this point, we've never done anything like in a human type context. These tools are difficult to deliver there, not that they can't be delivered there. So through endoscopy plus adaptive optics and so forth, I think there is a considerable potential for doing translational science with these types of tools, given that on your end that there's the right type of markers or whatever to be able to see what the microscopes could reveal. But given that, it's way too early. It hasn't been done yet, but there is the potential to go there.
Sure, just from what you've said is it's immediacy. It's yes. knowing straight away that the the biology has occurred that this cell is now restored in its function to be successfully transplanted.
Yeah, yes. So, and I'd also like to make another vote about organoids. I think they're wonderful. They're great systems for our microscopes, but I also think they'll be very critical in drug discovery as well, because we can have just much more physiological system to triage different things as we go along. Yeah.
Okay, now Salvador.
For Dr. Blau, two questions. The first one is you talk about...
There is a delay of the microphone.
There we go.
It's okay.
It's fine. It's working. It's working.
Was working. Oh, now is it? Now it is.
Okay. The first question is, you talked about the three types of stem cells, all positive ones, but there is a whole body of literature talking about cancer stem cells. Do you believe that there are cancer stem cells, and what's your opinion about the development of research in this area of cancer research? First. Second, I was very interested in your last experiments on prostaglandin E2. Do they suggest that one of the side effects of taking non-steroidal anti-inflammatory drugs in the adults might be the development of accelerated sarcopenia?
Cancer stem cells, definitely there's proof that they exist, and people are developing antibodies to target them. So once you can identify them, then you can work on drugs and antibodies to target them. So I think it's a very fruitful avenue of research, and they clearly exist. And your question about NSAIDs is very interesting. So it's definitely true that when we, for instance, give mice ibuprofen just after an injury, they become weaker. So they lose strength, not just maintain, but lose strength over time. So the prostaglandins are so crucial after injury for repair that, yeah, the stem cells absolutely require them. If we genetically ablate the receptor on the stem cells, we also lose strength in the mice. So it's one of the most crucial factors in muscle regeneration and muscle maintenance, and it may well be that sarcopenia is, it can be contributed to by chronic NSAID use. And many people, of course, who work out in a gym or go running, they take an ibuprofen afterwards. They're negating everything they did.
One reason not to take ibuprofen after the age of 60, perhaps.
Professor William Clark.
Of course, it's also another reason not to go running, right? So my question is for, again, a conversation between the microscope people and the macroscope people. And I'm sorry my colleague John Schellenhuber isn't here. He's written a very interesting piece drawing the potential parallels, but here we've got the people really doing it. And it seemed to me in the two presentations, at least three common themes came up. One was the problem of access. One was the problem of integrating machine learning into coping with the very large data volumes. One was the perhaps related issue of improving the opportunities for dialogue between the instrument makers and potential instrument users who don't quite yet know what the capabilities are. But equally, you don't quite know what their problems are, so you may not be designing the instruments exactly to match the use. What I'm curious is there any existing forum in which you microscopists and macroscopists regularly talk to each other about these analogous problems, and what's worked and what hasn't in trying to address them?
I'm not particularly aware of any such forum. I avidly follow the developments in astronomical research. And in fact, about once a year, I give a talk on the historical connections between astronomy and microscopy. And the take-home message of that talk is that microscopists are the retarded stepchildren of astronomers, because we steal everything from them 50 years after they do it first. Yeah, but still, certainly, in fact, Sarah and I were talking at lunch or dinner yesterday about detectors, right? I mean, there's a lot of commonality of hardware interests and so forth that, and again, I'm constantly inspired and learn from what they have to say. I don't know, in terms of a continuous dialogue between the two, whether that would ever pan out or contribute a lot other than just sort of an organic communications, but I'm certainly open to the possibility.
Well, I've asked Eric to solve our biggest problems for astronomy and detectors. Just kidding. But I was going to say that Earth is very bright, so anything looking down, they're not photon starved in any way. Whereas I understand from Eric that the photons interfere with what they're trying to do, so they try to limit light.
I'm not aware of any for either, you know, Earth observation really takes the optics developed in the general field of optics and applies them. And you know, I had a very similar slide to you once with the, you know, basically the only part of our satellite systems that would be recognized by people 50 or 100 years ago is the telescope piece, which basically looks the same. I mean, it's actually very specialized in how we make it to survive the launch and the things like that, but the actual design, from a basic principle standpoint, hasn't changed, whereas all the electronics and the radios and everything else looks unfathomably different from things that were around 100 years ago. But we really generally rely on other people to develop this stuff, and only recently has there been a few developments that may be relevant for us to do with filters and occultation systems across the primary optic that might start to do things that are a little bit interesting, and of course, until we get optical interferometry working well in space, which can then, you know, combine apertures and things like that, which could, of course, lead to different sorts of fundamental capabilities. Until that's possible, I don't think we'll see much advance over the next decade or so.
Now, we have one question by Noble Banada.
Thank you very much. As I listened to Professor Helen, and then I remembered your presentation, Professor Alon, yesterday, I saw a link. I don't know if I was right, but my question is, yesterday he talked about bioethics, and I didn't hear that from your side. How does that come in? Thank you.
There are definitely ethical issues. For instance, there are stem cell clinics that are being developed without any approval, and stem cells, we need to inform people about what's real and what isn't. There are things called mesenchymal stem cells that I didn't even discuss because they aren't real stem cells. They're connective tissue cells that are taken from different, there are clinics where you come off a ski slope at Vail with a hurt knee, and they'll take some cells from your fat and then inject them back, mesenchymal stem cells, into your knee. There's absolutely no evidence that that does any good at all. So there are ethical issues surrounding the use of stem cells and the regulation of stem cells and quality control, because the field could be very much hurt by some bad results. So far, they've been innocuous results, except, well, there have been some bad ones too. Where stem cells that were not approved, embryonic stem cells, were injected into the eye, and there was no reason to think they would ever function like eye cells, and they didn't. They caused blindness. So definitely there's strong ethical issues to be considered. I think in terms of generating cells, getting away from the embryonic stem cells has taken us away from this idea of embryonic destruction, because there are alternatives to consider. Was there something else that you were thinking of in particular?
Oh.
if I remember correctly from his presentation yesterday, I saw some linkages between what he's doing and what you are doing. Yeah. And I see as if there is a marriage in your research. Thank you.
Okay, Wolf.
I'd just like to draw the attention of the imaging people to a very, very burning imaging problem. It becomes clear now that we will only understand the brain if we are able to register from a very, very large number of neurons in real time in the living, behaving animal or human, if possible. Optical methods have now been developed. We can do it because the combination of modern microscopy and fluorescence makes it possible to see the electrical potentials of neurons, but it works only on the surface, and it's always invasive. So if we want a breakthrough in our discipline, we have to get away from the electrodes. We have to get away from putting metal into the brain in order to record from it, because it's not possible in humans at all. So MRI is too slow. The spatial resolution of the other electrical non-invasive techniques is just not admissible. It won't get any further. So I can only plea for an investment in non-invasive techniques that allow us to see the activity of nerve cells in vivo at a large scale.
This is exactly what my wife works on. So she's a neuroscientist who uses adaptive optics to do large-scale functional imaging in the mouse. But I would say that for all the improvements that have been made in that field in the last 4 or 5 years, we still have a very long way to go to get, even say pan-cortical or anything like that imaging of a mouse. Very long. I think it's going to happen in the fly first, actually, and work its way up. But I'm still concerned. I don't think there's been enough discussion of, even at the scale that it's done now, about how invasive it is. Yes, it's not electrodes, but there is a lot of energy being popped into the system to make those measurements. You're overexpressing a bunch of calcium indicators or other things in order to make the measurement, and I think we have a long way to go.
Okay, so now the very last question.
Helen, hi. Will you settle for us briefly the issue of cardiac stem cells, whether they exist or not? And if they do not exist and the heart doesn't have the ability to regenerate itself, then what are the prospects of developing cells that will help the heart, which is a huge unmet need for patients post-myocardial infarction with congestive heart failure?
It's a very good point. So maybe some of you are aware that at Harvard University, there's Dr. Anversa, who published about 30 papers that he just had to retract on cardiac stem cells. There sadly are no genuine bona fide stem cells in the heart, although we would definitely like there to be, because we need it to regenerate the heart. There really are none that are dedicated cells that will replace cardiac tissue. That said, it turns out that cells that you transplant into the heart, whether they are fat cells or other cells, they produce paracrine factors that aid the heart. They do no harm. And there are great efforts now in generating from these induced pluripotent cells cardiomyocytes that could be delivered and aid in cardiac function. So far in primate studies in monkeys, they've led to arrhythmias, and that's partly because they have a mixture of cell types of atrial and ventricular, and they need to find a way to differentiate them specifically down one path or another. But that's just a matter of time. I think it will happen, and that we will be able to deliver cardiomyocytes produced in the culture dish to aid in the function of the heart. So I'm quite optimistic.
Okay, so I want to thank you, the two first speakers of this section. We're now going for lunch, and we'll be here back at 2:30. So thank you very much for the two speakers.